Biostatistics questions are free USMLE points. They test the same core concepts every single time. But most students memorize sensitivity, specificity, and PPV formulas, but that's backwards thinking that wastes time and creates mistakes. The problem isn't the math, it's that you don't have a mental map. Everything blurs together and you can't tell what the question's really asking. But with the right framework, you'll spot the pattern instantly. In this high-yield lecture from our course, I'll break down the only biostatistics concepts that actually show up in test day. So again, with all of the PowerPoints that we're going to really ever go through, this includes all the recorded sessions on the course website. The key is the integration and application questions in the beginning. So with these questions, I've chosen things where it forces you to apply the underlying concepts in a way that if you can answer these questions, and again, the answers for the vast majority of these are in the PowerPoint themselves. So most of it's as easy as just copying and pasting it, making your own cards. But the goal here is that if you can explain these questions, you will understand the vast majority of the material that we're going to cover. So instead of having to make 50, 60 cards, you'll have to make maybe, a dozen cards, which I think is a much more tractable thing. And again, I think is much more valuable moving forward since the focus is on the application integration. I literally just got off Skype with a student that I worked with for step 1, who's now in her clerkships and studying for her shelf exam / step 2. And she told me that the integration and application methods and these sorts of questions are so valuable for step 1, but even more valuable for clerkships. The reason I asked her why, and she said that most of clinical medicine is variations of a story. So if you understand the underlying pathogenesis of presentation, you can apply those stories to slight variations. So if you understand heart failure, you can understand, okay, well, maybe this is heart failure from like left heart failure, or maybe this is heart failure from, I don't know, volume overload secondary to kidney failure or something like that. But again, the idea is that if you understand the underlying principles, you can apply it in novel contexts. This is exactly the same skill that you will be asked to do for step 1. So oftentimes you're going to be asked questions where you know the underlying knowledge, but students that are ultimately going to score 240 or above will be able to apply that knowledge in a novel context, right? So we've all heard stories of students who get out of step 1 who say, oh my God, none of the questions were questions that I saw in UWorld. I don't understand. These weren't things that were in first aid or blah, 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 blah. The reason why they say that is because they focused mainly on memorization and they weren't focused on learning how to apply it in a novel context, which means when they saw questions that were variations on things that they already were supposed to know, they fell very flat because they hadn't practiced applying and integrating it. So if you start from the integration application, which we're doing here, it makes it much easier for you once you're just taking your exams, as well as my student pointed out, once you get to clerkships in understanding actual clinical medicine. Okay, so let's get started. There are some themes that I want to start with. So these are fundamental themes, right? So again, I think that one of the biggest problems with statistics is there's so many details. And so it's really easy to just start thinking, oh, I just have to memorize a bunch of things. I would rather think about what in a big picture sense, what are we actually looking at, right? So medical studies, really, they're just looking at 3 things, right? They're looking at exposure. They're looking at outcome, which might be disease, might be like the treatment of the disease, and then somehow the relationship between those 3 things. At core, if you think about all the major studies that we're going to talk about today, that's it. When you boil it down, they're looking at exposure, outcome, and their relationship or lack thereof. Also at core, research studies really, they're just asking whether 2 or more groups are different. That's really what every single research study is asking. 2 groups, are they different or are they not different? The other thing is I think it's important to understand, statistics definitions are just, like we said before, it can be so mind-numbingly difficult, right? So to get to this point, and again, I'm by no means an expert in statistics, right? I don't have a PhD. I haven't done like a master's in this stuff. right? So to get to this point, it's taken me years. I did pretty well in statistics in medical school and on step one. And I don't think you have to be an expert to do well on these exams. The key is to understand fundamental principles that we're going to go through. Okay. All right. So let's talk about study design. So Aparna, can you tell me, what is a retrospective study?
It's a study that you go back or you look back in time.
Yeah, sort of a softball.
Okay.
Right, yeah. So we're looking back in time. So how about Jasmine? Can you tell me then, what's a prospective study?
A prospective study is where we're gonna choose a point and then look, for example, an exposure and then see how they will develop the disease in the future.
Sure. Yeah, exactly. So it's looking, instead of retrospective, which is looking back in time, prospective looks forward in time. Okay. And so Jolan, what's an observational study?
An observational study is where the exposure is not really under control of the researcher, so it's kind of independent.
Yeah, perfect. Yeah. So if we think of a study as being exposure, outcome, and relationship between exposure and outcome, or lack thereof. An observational study, this is a definition I had to think a lot about, right? But really, an observational study is really one where the exposure is under little or no control of the researchers. So if that's what an observational study is, then Mike, what would a interventional study be?
Maybe like adding something.
What do you mean adding something?
For example, adding a drug.
Okay, so but if an observational study, if we're thinking about exposure, outcome, and the relationship between those two, what's another way of thinking about an intervention? So your definition is, it's a reasonable description, but like fundamentally, what's different about an observational and interventional study?
Control, I guess, versus
Control over
the exposure.
Yeah, exactly. Essentially, an interventional study is where the researchers are controlling exposure, right? So as Mike pointed out, oftentimes this is a treatment. But again, at core, an interventional study is where the researchers are controlling exposure. That's it. Okay. So those are pretty, hopefully, straightforward questions. Now, what's the major, Nikki? What's the major kind of retrospective observational study that you're most likely to see for the USMLEs?
Would it be a cohort study?
So it is possible to have a retrospective cohort study, although that's not common. And you will almost never see that for the USMLEs. So we're talking about a retrospective study.
Case control?
Perfect. Yeah. So it's a case control study. So a case control study, again, is a retrospective study. And again, it's observational. Nikki, why?
Because we're not controlling the exposure or like the treatment for it.
Well, so there's no treatment. So again, we're not talking at all about treatments in the vast majority of these cases. So what the point is that you're not controlling, it's observational because you're not controlling the exposure. Okay. And so what's the major kind of prospective, is it Yashna? What's the major kind of, sorry, how do you say your name?
Yashna.
Yashna, perfect. Okay, so Yashna, what's the major kind of prospective observational study?
So would that be a cohort study then?
Yeah, so that would be a cohort study. Perfect. Okay. And so, Yashna, what's the major kind of prospective interventional study?
Not sure.
Okay. Patricia, can you help us out?
The prospective interventional study is cohort study, but analyzing relative
risk.
risk.
Observational, right? So what would be an interventional study? Honestly, there's only one kind of major interventional study with different kinds of variants for step one, at least, and the USMLEs generally.
I don't know.
Anyone?
Sorry.
Randomized control.
Perfect. Yeah. So a randomized controlled trial is the major kind of, so whenever there's some sort of prospective interventional study, right? So again, where they're controlling the exposure, the major kind of study you're going to see every single time is a randomized controlled trial. Okay.
Can you explain a little better the case control study? Like, how would you know are you just basing it sort of off the definition of what the case control study is? And then that would be the ideal retrospective? observational study?
It's a great question. You're saying like study choice. Why is that so I'm not saying it's the ideal kind of retrospective observational study. That's actually not what I said. I just said what's the major kind of retrospective observational study you're most likely to see on your exam. I don't want to go. So again, I am intentionally going to limit the scope of this because, I mean, as you've probably seen when you're trying to learn statistics, there are so many different kinds of studies and there's so many variations on the different kinds of studies. So I don't want to tell you every single possible kind of study. I just want to go big picture, at least for now, big picture and explain what the major studies that you're most likely to see. Does that
Okay.
So case control studies are retrospective observational studies. They are also the by far the most common retrospective observational study you're likely to be tested on. Does that make sense?
Yeah. Okay. Thanks.
Okay. And then there's one other kind of study that you're most likely to see, and that's a study that's looking at one particular moment or one particular snapshot in time. So Jaiho, can you tell us what that kind of study would be?
Cross-sectional studies.
Yeah, cross-sectional study. Perfect. So next I want to talk more about these particular kinds of studies. So Haley, hopefully we can answer some of your questions with talking about what exactly a case control study is. Okay, so again, Haley, what are the three elements that medical studies typically look at?
Exposure, outcome, and the relationship.
Yeah, perfect. Exposure, outcome, and relationship. Okay, so Haley, how does a case control study typically work? How is it usually set up?
So those are the ones where something has already happened and you're kind of gathering them as a group and then looking backwards to see what they might have been exposed to.
Okay, so this is like one of the most common ways that people talk about statistical studies, at least in medical schools. So the pro of the way that you just described it is that technically what you said is true. The con is, what's the issue with the way that you defined it?
Not specific.
Yeah, exactly. Like if you actually were like trying to create an instructional manual, like you would be nowhere near giving enough sort of details to actually understand what it is. The problem is, so what happens then is that when people try to teach this, as you've maybe seen when you try to read about this stuff, is that then they give such technical definitions that you're like scratching your head and you're like, wait a minute, I don't understand what they just said. Technically they used the English language, but I didn't really understand it. So let's try and find like a happy medium. Can someone give us a slightly more technical definition, but that still is like understandable in plain English for what a case control study actually is?
Sure.
From what? Oh, sorry, go ahead.
Go ahead.
Jessica, go ahead.
Oh, okay. So a case control study is when you look at people who have a disease and you're going backwards in time to see if they were exposed to something versus another group of people that have the disease but didn't maybe have the exposure looking back in time, and you try to match them based on like their age or their race and other factors that you can't control for when you look back.
Perfect. Yeah, exactly. Or that you can try to control for, right?
Yeah.
So
right.
So you're looking at people. So again, studies at core are looking at whether two groups are different or not different, right? Again,
Yes.
So remember, critical theme. So we're taking two groups. Those two groups are a group that has the disease and a group that does not have the disease. Then you're going backwards in time again. So retrospective observational study, right? Because we're not changing the exposure. And then you're looking at the exposure in the group that has the disease and looking at the exposure in the group that doesn't have the disease. Okay. Does this make sense? Yes? No?
So are you saying that the commonality between the two groups is their exposure?
The commonality between the two groups? No, not necessarily. Well, so you're assessing the exposure.
Okay, so do both groups have the same outcome then?
No. So the point is the two groups do not have the same outcome.
Okay.
Right? So you've got one group of people that have one outcome and one group that do not have that outcome. So I think it's a lot easier. So my goal with this is to give as many examples as possible, because I think that it's a lot easier once you actually go through examples. So who am I gonna pick on? Because this is kind of tough. Actually, Nikki, I think, wanted to speak. So Nikki, so let's say that we were trying to prove, or we were looking at the relationship between developing brain cancer, and cell phone usage. How would you design a case control study that would ask this question? Is there a relationship between cell phone usage and brain cancer?
So for this, would we be looking at people who have brain cancer and people who don't, and then seeing if their exposure to cell phones, like if they've been exposed to cell phone usage or how much they've been exposed to cell phone?
Yeah. Okay. So let's say that we think that there is a difference between these two groups. Again, theme is you're looking at whether these two groups are different or not different. Let's say that let's assume that they are different. So what would you expect the results to be if there was a positive relationship between cell phone usage and brain cancer?
So cell phone use,
No, go
so
ahead, Peggy.
increased cell phone usage would lead to brain cancer.
So that is not true. That is not that is not the outcome that would actually happen. And it is exactly what I expected you to say, because that's what everyone says in this situation. Okay, so we'll talk about that in a second, but let's make sure that we understand the study design first. Okay, so we have brain cancer patients, and then we have matched controls, right? So ideally you would match someone as many things as possible, right? Like age, sex, gender, whatever, right? To try to control for those other variables. And so you have brain cancer patients and then matched controls without brain cancer, right? So these are the outcomes. You're starting with the outcome. Then you look back in time to assess exposure. So you're looking back in time and you're asking the question, okay, how much cell phone usage was there in brain cancer patients? And how much cell phone usage was there in not brain cancer patients? Okay. This is, to be honest, probably the most confusing study this is by far the most confusing study of all of them, by far. So I want to make sure that we're all on the same page here, because everything that we talk about after this is going to build on this. So I don't think I explained this particularly well. So I want to make sure that I clarify things before we move on. So what questions do you guys have about case control studies before we move on?
I have a quick question, Alec.
Please, yeah.
So basically what I said before, saying that increased cell phone usage would lead to brain cancer,
Yes,
would this
You
be
can't-
more like,
You can't prove that with a case control study.
okay, so what would this be proving?
We'll talk about that in a second.
Okay.
It's basically, the positive relationship would be brain cancer patients are more likely to have used cell phones a lot in the past.
Okay.
That is very subtly different. It's not the same, right? Most people assume that means the same thing. Those are not saying the same things. What I said was brain cancer patients had a lot of cell phone usage in the past. That's different from saying using cell phones is associated moving forward with a higher likelihood of developing brain cancer.
Wait, Alec.
Yes, Joanne.
I was looking forward in the PowerPoint, and you were saying that an odds ratio is how you measure case control versus relative risk. So if
Let's talk about that later. Can we talk about that when it comes up?
Sorry. Okay.
I want to talk about that. This is like such an important part. I don't want to understanding how a case control study works is critical. So if you guys do not understand that, this is the time to ask.
Well, I was trying to figure out if that would help understand, because it is really subtle, the difference between going backward in time versus going forward. So
I think
that's
it
why I
will.
brought it.
Yeah, I agree. That's why I'm exactly. Understanding the difference between odds ratio and relative risk, I think, will help explain the difference. But I want to talk about the definition of case control study first. Any questions, or is this crystal clear? Clear as mud. Okay. All right. So what kind of bias is most concerning for a case control study, and why would that make sense? So Jalan, what kind of bias would be most concerning for a case control study?
I guess it's a recall bias, because it just depends on whether or not the person knows they had the exposure.
Okay, so give me a little bit more. So you're right? So recall bias, but like, what exactly is recall bias, and why specifically would this be most concerning for a case control study?
Well, so if you're doing a case control, I'm assuming you start with people who have brain cancer, and then you ask them, well, do you use cell phones? How much do you use it? How often? And then you look at people who didn't have brain cancer and you ask them the same question.
Perfect. Yeah.
So then if they recall it incorrectly, you don't really know if that's, I mean,
Why
that
would you
kind
be
of.
more likely? Why would a case control study lead you? Again, this is a common step one question. Why would it, or USMLE question in general? Why would a case control study itself, like the setup of it, make recall bias specifically more likely?
Alec, is it because you have to try to remember stuff
Yes.
that happened in your past?
Yeah, exactly. And so why is that a problem here?
Depends on how well you can recall things, especially if it goes back more than like 5 years.
Yeah. Well, the other thing is remember, like, people have probably heard in the media that, oh man, cell phone usage leading to brain cancer, right? So if I have
Right,
brain cancer, what
right.
do you think I'm going to say? So you have this study, and maybe you tell them what it's about, or maybe you don't, but like, these people know that they have brain cancer, right? So you go in and you ask them, hey, how often did you use a cell phone when you were little? Was it more than your friends? How many hours do you think that you were using it? What do you think that someone with brain cancer would say, right? Because someone with brain cancer is thinking like, oh man, was it something I did? Was there some, and they probably thought about this like dozens of times, right? Like, was there some, like, was I exposed to something? And then maybe they're thinking, gosh, maybe like when I was a teenager, maybe I just used like all those times that I was on my cell phone. Maybe that's what did it. As opposed to someone that didn't have brain cancer, they're probably not thinking too much about like what exposures they may have had when they were little. Does that make sense? So this is like a classic sort of thing. So recall bias for case control studies. And the reason specifically is because A, the way that it's set up, and B, the fact that it's retrospective, right? It relies on people's recall. So where are you most likely to get recall bias? When people's ability to recall it is going to affect your results. Okay. So yeah, in our brain cancer study, again, so if you've heard that cell phones may be linked to brain cancer, again, if you are a brain cancer patient, it's not unreasonable to think that you'd be more likely to recall using cell phones in the past. It's sort of like when there's no evidence to suggest that epidurals cause lower back pain. Zero evidence, none whatsoever. But guess if you were to ask someone that had like low back pain, like, oh, did you have an epidural in the past? Guess what? They're going to remember that epidural. I promise. I see this all the time as an anesthesia resident. Like, it's just, this is like, you're just going to think like, oh my gosh, must have been that epidural. Even though like for labor epidurals, which is the time, probably the most common time that we're doing epidurals in a population-wide way, right? Like they're going through labor, they're on their back in a weird position. Like there's so many other things, but again, they're going to remember the epidural. Okay. All right. Editha, how do you measure the relationship? Right, again, so studies are outcome, exposure, and relationship. So how are we measuring the relationship between the outcome and the exposure in a case control study?
Odds ratio.
Perfect, exactly. And Editha, so this is like probably the hardest question I'm going to ask. So it's probably unfair to you, but can you try and explain in plain English what an odds ratio is?
Okay. Odds ratio. Okay, I just watched the lecture that you recommended on your website. So the guy said it's one number over one number, and then it's the ratio, the difference between exposure over non-exposure.
So this is why, so you'll notice if you read through the PowerPoint, I tried really hard not to use equations, in part because I want you to understand, because sometimes they will ask you, and eventually we will go over some of the equations, but I want you to understand what these things mean, because more often than not, they're going to ask you definition type questions. So if you don't understand the definition, it's really hard to understand it. So can you think Eric, let's have someone help maybe. What is the odds ratio? Like, what is it actually saying?
I can try to answer this.
Please, let's do it.
Okay, so an odds ratio is trying to compare the two groups. So we were looking at the people with the disease versus the people without the disease. So we're looking at the odds that the group with the disease was exposed to a risk factor versus the odds that the group without the disease was exposed to a risk factor. Yeah.
Perfect. Yeah, exactly. So again, that is so, but why is so? Okay, so that was good. So what Jessica has just volunteered herself for is to help anyone with understand statistics for the USMLEs. She just volunteered. I'm just joking, half joking. All right. So it's the likelihood that someone with the disease, right? So a particular outcome had a particular exposure, right? So again, this sounds like it's really straightforward, but this is probably the most difficult definition to understand in this entire PowerPoint. Okay. So Jessica, can you explain what would this, so actually let's see. So the way that I test how well we've explained something is I ask someone who didn't know the answer afterwards to see, can they explain it? So who are we gonna, how about Caitlin?
Okay.
So I don't know if you knew this or not, but can you explain to me then, so what would the odds ratio represent in our brain cancer cell phone example?
No, I do not have a good grasp of this. Used to have it memorized, but coming back to it now. So I would guess that for odds ratio for this, it would be I want to try to do this without looking at your PowerPoint. The odds that the population with brain cancer with exposure to, or the likelihood that the people with brain cancer had exposure to cell phone use versus the non-brain cancer population with cell phone use.
Very good. That was actually really good. Wow. Okay. Nice. Does that make sense to everyone? So in patients with brain cancer, what's the relative likelihood of exposure? Oh my gosh. The relative likelihood of exposure relative to patients who do not have brain cancer. Okay. So I want to, does that make sense? So this is different from, I can't remember who said the definition. Maybe it was, I don't remember who said it before. Who said that it was the likelihood of developing brain cancer if you had been exposed to cell phones. Do you see how this is subtly different? So if you say, so you're starting, the previous definition was, right, the incorrect definition was, if I am exposed to cell phones, how likely is it that I will develop brain cancer in the future? That is not what an odds ratio is. An odds ratio is, if I have brain cancer, what's the likelihood that in the past I had exposure to cell phones? This is one of those things that you want to repeat to yourself, I don't know, probably 5 times in the mirror tonight while you're like brushing your teeth. Like, it's one of those things that it sounds almost identical, but it is very different but it's very subtle. It's a very, very, very subtle difference. One is looking forward, the other is looking back. We're going to return to this theme once we talk about cohort studies. But again, I want to just, if your head is kind of like numb and spinning right now, that makes a lot of sense, because that's like what my head was like when I thought about this for a long time. Okay, so let's talk about a cohort study. So in this case, a prospective cohort study. As sort of like a side note, there are retrospective cohort studies, but you will almost never see, I've never seen a retrospective cohort study in any standardized exam for medical school. Never ever. It is almost always going to be prospective. Okay, so Mike, what is a cohort study?
So basically, I guess pick like the back example, someone with brain cancer, someone without brain cancer, and follow them forward in time rather than back in time.
Nope. Try again. So again, give me more. So that's not quite. Again, so remember, what are the three parts of all studies?
So exposure, outcome, relationship. So maybe someone with an exposure and someone without. And follow them
Perfect.
forward.
Good. Yeah, exactly. So again, whereas a case control study is starting with the outcome and looking backwards to look at the exposure, a cohort study looks at the exposure. So a group with an exposure and a group without the exposure, and follows them prospectively to assess the outcome. Does that make sense? Again, subtle differences. So this is, I think, one of the reasons why people struggle with statistics so much is because the words sound so similar that we can trick ourselves into thinking that we understand it. But then when you're actually faced with a question, you're like, oh my God, I have no idea what's going on. Mike, does that make sense?
Yeah, thanks.
Okay. So in the case of our brain cancer and cell phone usage study, how would you design a cohort study? Let's go with Emma. How would you design this study?
So take two groups of similarly matched people and expose one to a risk factor and see whether they whether the rates of developing brain cancer are different.
Not quite. What kind of study did you just describe?
That's a good question. Perspective.
So it is a prospective study. Is it observational or is it interventional?
Interventional.
Yeah, because what you just described was where the researchers are controlling the exposure. So remember, a cohort study, is it observational or is it interventional?
Observational.
Observational. Okay. So try again. So in our case, right, how would you design a cohort study? Because you designed an RCT, right? You designed a randomized.
Right. Okay. Yeah. I'm not sure on this one then.
Okay. So Emma says exposed to phone versus no exposure to the phone and go forward to see whether they have the disease. Perfect. Yeah. So in other words, you would have two groups. Again, studies are looking at whether two groups are different or not. So the two groups you would look at are, were they exposed to a high amount of cell phones or were they not exposed to a high amount of cell phones? And then follow them forward and see how many of them develop brain cancer in the two groups.
I don't understand. Oh, okay. So you don't match them exactly. You match them except for cell phone usage.
Yes, exactly.
The difference is that you're not applying the risk factor. It's okay.
Correct. Yeah, exactly. Yeah. So the way you described it, you randomized the patients and then you randomize them to either getting cell phone exposure or not getting cell phone exposure. That by definition is a randomized controlled trial.
Okay, I understand.
Interventional, you're controlling the exposure. No, it's great. I'm glad that you brought that up. But yeah, so what a cohort study, you are controlling things. You're controlling everything except for the cell phone usage. Ideally, that would be the ideal cohort study. Everything else is the same except for one group is high uses of cell phones and the other group does not. Much easier said than done, but that's the ideal. Okay. Jasmine, how would you measure the relationship between the outcome and the exposure in a cohort study?
Isn't there a relative ratio?
Yeah, relative ratio, or I guess a lot of relative risk ratio.
Oh, yeah.
It's a lot of, I think usually they say either relative risk or risk ratio. There's a lot of like subtleties here, but these are essentially equivalent. So Jasmine, can you tell me what exactly is a relative risk?
Would that be So it would be patients who were exposed to it developed brain disease over patients who were exposed and did not get the brain cancer?
Oh, you're giving me like the equation.
Okay.
No, that's actually not how you would design. No, I'm asking like in words. What does the relative risk tell you?
Oh, what is the risk of a patient developing brain cancer if he's exposed to telephone use? Would that be an example of one?
Yeah. Essentially, yeah. So it's the ratio, or it's the risk of developing disease among people who are exposed over the risk of developing disease among people who are unexposed.
Okay.
So, Jay-Ho, in our brain cancer cell phone example, what would the relative risk represent?
So people who use cell phones, do they have more incidence of brain cancer than people who don't use people who don't use cell phones?
Yeah, perfect. Yeah, exactly. So in other words, in people with high cell phone exposure, what's the probability that they develop brain cancer relative to people developing brain cancer with low cell phone exposure? Perfect. Exactly. Okay. So odds ratio versus relative risk. This is, I think, one of the most challenging things to understand. And again, it gets back to Jolan's point earlier, which was if we understand the difference between this, actually the tests themselves, case control versus cohort studies, themselves should make more sense. So again, I want to make this very, very clear. Okay, but because it sounds almost like these definitions are the same, odds ratio and relative risk. So they're not. So let's talk about those definitions again. So odds ratio, who wants to walk me through what an odds ratio is?
So the odds ratio, you're going to look at the people who have the outcome and then go backwards and determine the likelihood that they used cell phones or had the exposure.
And then relative risk.
And then the relative risk is going to be what's the chance that your use of cell phones or the exposure, what's the risk that you're going to develop the outcome or the brain cancer compared to those who do not use that and have the outcome.
Yeah,
I
perfect.
don't know if that was exactly right.
Okay, so questions about this. Again, this is like probably the most like mind-numbingly difficult thing to understand in probably this entire PowerPoint, right? But if you understand this, the difference between an odds ratio and a relative risk, you also, I think by extension, really understand the difference between a case control study and a cohort study, which is kind of cool, right? Again, this is like the textbook definition of an integration and application question. Because if you, by understanding this one question, you have to understand what an odds ratio is. You have to understand what relative risk is. You have to understand the difference between a case control and a cohort study. And you only have to make a single card to do it. You only have to review a single card. And you'll be able to assess and retain all of that information. It's pretty powerful. But again, I think it speaks to the power of having integration and application questions. So before we move on, I want to make sure that we're all on the same page because this is like the most difficult thing we're going to talk about.
Can I make sure that I understand them?
Please, absolutely.
Okay, so in odds ratio, we're looking back in time and compare the groups to their exposure to cell phones. Is that correct?
Kind of. So give me a little bit more specific of a definition, though. So again, you're bordering on like the vague, unclear definition.
Yeah.
Right?
Okay. All right. So for odds ratio, we're looking at, so there are two different groups, aren't they? Like one with brain cancer and one without brain cancer. And then we look back in time to see if each of the group has had a lot of exposure to cell phone use, or I don't know how to say it.
Yeah, no, that's exactly it. Yeah, you have two groups. One group has brain cancer, one group does not. You go back in time and you ask, what is the likelihood of exposure in people with brain cancer to cell phones versus what's the likelihood of exposure to no cell phone, or likelihood of exposure in people that do not have brain cancer.
But we're not concerned about the results, because they may or may not have the same exposure to cell phones. Correct?
You are not.
We're not
The question that you're asking is how much exposure do they have? You're controlling the outcome.
Oh.
In the sense of like, right? Like one group has brain cancer, one group does not. Right? So the question that you're asking is, were they exposed to cell phones or not?
Oh, I see. Okay.
Does that make sense? As opposed to relative risk, or a cohort study where you're separating them based on exposure. So one group is exposed to cell phones, the other group is not. And then you're following them forward and saying, okay, how many of these people in the exposed group develop brain cancer? How many people in the not exposed group develop brain cancer?
So in odds ratio, we're separating them based on the disease. One has the disease and one doesn't not.
Correct. The two groups you're looking at, one of them has the disease, one of them does not.
Okay.
A cohort study.
Yeah. Whereas in relative risk, we don't know if they have the disease or not, but we're comparing the exposure.
Be a little careful. So it's not the odds ratio itself where you're looking at this, the relative risk. It's the studies that use odds ratio relative risk. So a case control study that you separate the two groups based on disease or no disease.
Oh,
And in a cohort study, you're separating them out based on exposure or no exposure.
okay. All right. Okay. I was using the wrong.
Does that make sense?
Yeah. Okay. All right. Thank you.
Yeah. Other questions? All right. So again, it's just like a bucket full of fun, right? Null hypothesis, alternative hypothesis. I think this stuff is like more interesting when you think about like the big picture. Like I'm a very big like big picture fan. Like I like to think of like the fundamental themes, right? So again, the key theme here again is that really like at core, research studies are asking whether two or more groups are different. That's it. That's really what like most studies are designed to do. They're asking, is this group different from this group? And by how much? And what's the likelihood that they're different? Right? But that's it. At core, you're just asking, are these two groups different? So it sounds super simple. However, it's actually much more difficult in practice, which is why there was a study not too long ago in I think it was in like PLOS One or something, like a pretty major journal where it said like, I think it was a very incendiary title. It was like something like the majority of published research studies are false or something like that. You should look it up sometime. It's a very interesting article. So the issue is like, how do we know if two groups are different? How do we know? So there are these things called null hypothesis and alternative hypothesis. Who am I going to pick on? Yesna. Yesna? Yesna?
Yeah.
What's the null hypothesis?
So that would be there's no difference between the two groups.
Yeah, exactly. Yeah. So again, our research study is just asking us, are these two groups different or are they not different? Right? They're not saying, are they different or are they the same? That's not what they're saying, right? They're just saying, are they different or are they not different? So null hypothesis says that they're not different. So Patricia, unmute yourself and tell me, what is the alternative hypothesis?
When there is difference between the two or more groups.
Yeah, exactly. So the alternative hypothesis is saying there is a difference. Null hypothesis is no difference. Alternative hypothesis says there is a difference. Perfect. Okay, so let's come up with some examples. Right, so in our brain cancer cell phone study, what would the null hypothesis be, Marlene?
It would be the patients with, there is no difference between the patients that have brain cancer and the patients that.
Well, so let's think about this in terms of like a cohort study. So for a cohort study, I should have specified this. In a cohort study for our brain cancer cell phone example, what would the null hypothesis be?
That there is no difference between, because that the cohort is measuring exposure. So there wouldn't be any difference between the group of patients using the cell phone more often than the patients that are not using the cell phone that often.
Close, you're close. So not that there's absolutely no difference, like period, but there's no difference relative to what?
To having brain cancer.
Perfect. Yeah, exactly. So say it one more time. So in a cohort study, what would be the null hypothesis?
In the cohort study, there would be no difference in patients with brain cancer that have used cell phone often. I'm sorry. I just
no, that's right.
a little bit. I have the idea though. But
No, but it's important to I mean, for all of you guys, it's really important to be able to talk this out.
Yes. Let me try one more time. In a cohort study, there wouldn't be any differences between patients who develop brain cancer who were using cell phones often with those who the same that develops brain cancer that were not using the cell phone often.
Good. So in other words, would it be fair to say that the rate of developing brain cancer in people that use cell phones a lot would be the same as the rate of developing brain cancer in people who didn't use a lot of cell phones.
Yes.
Is that fair?
Cool. Yes.
Perfect. Yeah. And then who am I going to pick on next?
Wait, I have a question now.
Yeah, please.
So now you're saying rates. Before, I thought before it's just whether you have brain cancer or you don't. Oh my gosh, I'm getting confused.
You're thinking of a case control study. So sorry. So let's be very clear here. So in our brain cancer will be for a cohort study, right? So for a cohort study, this is true.
Okay.
So a case control study, remember, is different. Case control study is you're looking at people that have the disease versus people that don't have the disease.
Okay.
And then you're going back in time and seeing were they exposed. So the null hypothesis for a case control study would be in people that have brain cancer and people that don't have brain cancer, there's no difference in the odds that they were exposed. The odds are the same. They're exposed to cell phones, like high amount of cell phones.
Okay. Okay. That is for the case control.
That would be
study.
for case control, but that's not what we were talking about.
Okay. So now for the cohort study, we're talking about, okay, because we're basing that on exposure.
Yeah. So in cohort studies, you're looking at your two groups are were they exposed and they were not exposed.
Okay.
And
I
then you're
see.
following them and you're looking at the outcome.
Okay. All right. Sorry. Okay. Yeah.
Yeah, they kind of, this is the way that I'm looking at it, and it might help some other people explain, and correct me if my logic and all this is wrong.
Sure.
But so with the cohort studies, our main concern is seeing what the outcome is going to be.
Yes.
So then you keep that same principle and we're applying it to the null hypothesis. So our outcome that we're concerned with is brain cancer. So that's what our null hypothesis is going to relate to. And that there's no difference between the brain cancer rates because that's our outcome and that's our main concern with the cohort studies.
Yes. That was technically very good. I wonder, I personally, if I didn't already understand it, I would have had a hard time learning it from that definition. Just like I have a hard time learning any statistics from these definitions because they're, I don't know, but I might be wrong. That may have helped.
That's just what I've been doing to keep in mind.
I think it's good. No, I think it's great. I just think like there was, I don't know that I would have, it was just very technical, which is good, but I don't know. I find statistics very challenging. So I don't know that would have been the thing that tipped me over. I don't know. Edith, did that help?
Thank you anyway, Haley. But
it's fine, but then I just thought I would try to.
I still don't get it yet.
So what don't you understand?
Just the difference, just to differentiate. I guess I don't know how to say it.
So I think the thing that you're struggling with, my guess is, like all of your questions have sort of come back to the difference between a cohort study, which is, again, I completely understand. This is the hardest thing to understand.
Yeah.
So what is the difference between a cohort study and a case control study?
All right. So case control is based on the disease. And then we're looking back in time. Is that correct?
Yeah, it's true, but that's really vague. The problem is that I think that your definition is so vague to the point that it may not help you. So, like, yes, that's true. What you said is technically true, but it's not very specific. So be more specific. So what would a case control study look like in our brain cancer cell phone example?
Okay. We are comparing two groups of people. One group has brain cancer, the other group does not. And we are looking at each group's exposure to a lot of cell phone use and see if there is a difference.
Yeah, exactly. Yeah. You have a group of people with brain cancer and a group of people without, right? So you're starting with the outcome.
Okay.
You're looking back in time and you're saying, how much exposure did they have? Is there a difference in the exposure?
Okay. All right.
As
Okay, so
opposed to, that's a case control study. As opposed to a cohort study, which is what?
all right. So cohort studies, we are basing that on exposure. So we have two groups of people who have been exposed to a lot of cell phone use, and we are looking
No.
to see.
No. So you're separating them based on exposure. So one group has a lot of exposure, and the other group does not.
Oh, okay. So, okay, we're separating the groups. Okay, one group has a lot of exposure to a lot of cell phone use. The other group does not have a lot of cell phone use. And we are looking to see if both of them develop brain cancer.
We're looking at the rates of developing brain cancer in people that use a lot of cell phones versus people that don't use a lot of cell phones.
Okay. All right. Okay.
So again, so if you don't understand this like perfectly right now, that's okay. Because honestly, I didn't understand this for like years. Like it wasn't until I really like had to start teaching this as a tutor that this really made sense to me. So I'm sure you're not the only one that's struggling through these definitions. You're just the most honest.
Sorry. Okay.
But it's one of those things that, again, I would go through this again and again, and I would try and explain it to like your family or something. Yeah, like really try to come up with examples.
Yeah. Okay. All right.
Aparna, can you tell me
Yes.
in our cell phone example, what would the alternative hypothesis be for a cohort study?
Okay, that means that there's some difference between the rate of brain cancer development in people who use cell phone versus the people who don't use cell phone.
Perfect. Yeah, exactly. Yeah. Excellent. Okay. How are we feeling? Are we like, this is like wonderful, I understand this so much better now? Or are we like, oh my God, this is, I didn't come to medical school to do this? Or maybe you feel both of these things. That's probably how I would feel in this situation, hopefully.
To me, this discussion really helped concrete the stuff that I learned from books and videos. So this discussion really dissected it sort of and helped it.
Perfect. I'm glad.
I agree.
You're like a ringer. That's great.
Alec, you opened my mind. Absolutely. Thank you.
Excellent. Well, thank you, Patricia. All right. Well, let's see how much I opened your mind. So Patricia, can you tell me? So if we know that studies are, the whole point is that we're trying to to see as a group, are two groups different or are they not different? Okay. So starting from that theme, what exactly does the p-value mean, Patricia?
And p-value is related with odds ratio. Let me see. Alpha with error type 1 and beta error type 2.
Okay, but give me like a plain English definition of the p-value. Like, what exactly does this mean? This is hard. This is probably the second hardest question I'm asking in this entire PowerPoint.
Let me see.
If you need help, you can call a friend.
Remember, the lectures that you told us to watch, the guy said it in a very simple way. Doctor, he said that it was a p-value with a chance of the event happening by random, by chance.
Yeah.
Is that correct?
Yeah, exactly. So again, the question that we're asking, again, if you just remember, the question that research studies are asking is, are these two groups different or not? The p-value is telling us how confident we are that the two groups are different, or actually different, versus it's just due to random chance. So a p-value is saying it's the likelihood that the difference seen between two groups is due to random chance. They love these questions. Love questions on p-value. Right? So again, let's take a step back. So if the question we're asking is, are two groups different? Right? Really what we should be asking is, okay, how do we know? The question is we don't. We just have We just have, all we have is, one of the things we have is the p-value. The p-value tells us, so in other words, let's say that the rate of developing brain cancer in people that use a ton of cell phones is like 0.2%, and the rate of developing brain cancer in people that don't use a lot of cell phones is 0.1%. So we've got a cohort study, prospective cohort study. Okay. The p-value, so those numbers are different, 0.2% versus 0.1%. Those numbers are different. However, maybe it's just random. Maybe it's just like a random chance. Maybe like one person maybe there's like, I don't know, 3 people in the study, and one person happened to have brain cancer. I don't know, whatever. It wouldn't be 3 people, but let's say that there was a very small number. So the p-value could be really high or could be really low. What the p-value is telling us is what's the likelihood that the difference that we're seeing between 2 groups is actually due to random chance. So in other words, what would it, who am I going to pick on? Isabel. What would a p-value of 0.05 mean? Right? Because that's sort of like the standard that we use.
So it's a 95% confidence interval, which I believe is 2 standard deviations within 2 standard deviations, I mean.
No, but like the 0.05, what does it actually mean?
What does the 0.05 mean?
Yeah, like what? So what does a p-value of 0.05 actually mean? You just gave me equivalence of like that, but I mean, I'm actually asking specifically, like, what is? Because they're gonna push you on this on your task. I guarantee. This is a very
like
popular statistic.
Point, or so like a 5% chance that the result that you see that looks like it's
What
real.
result are you talking about?
So the p-values, it relates to whether or not you agree or disagree with your hypothesis. So
oh, man, that's such a good med student answer. It's like, it sounds so fancy, but it is so vague. I don't actually know what you're saying.
No, neither do I. I don't know.
All right, let's phone a friend. Can anyone help? Again, this is really tough. Hannah, you want to give it a shot?
Yeah, let me see if I can do it. The 0.05 is that there's a 5% chance that what you're seeing between the 2 groups, like the difference you're seeing, is just random chance. Like there's actually no connection. It's just random.
Yeah, exactly. Yeah. Again, remember. So again, like once I realized that really all studies were doing was asking, are 2 groups different? This all made a lot more sense to me. Right? So we're saying that, so in almost every case, right, if you're comparing like rates of things to each other in one group versus another, the rates are going to be different, right? You're never going to have 2 identical values. So you're never going to be able to say like from those values themselves whether the 2 groups are actually different, right? Does that make sense? Like, so even if, let's say that they were both about 0.1%, right, for developing brain cancer. Let's say it was like 0.12 in the cell phone group and 0.11 in the low cell phone use group, right? Those numbers still aren't the same per se, right? So what you have to ask is that difference real or not? In other words, is it due to random chance, which, I mean, the difference between 0.12 and 0.11, probably yes, right? Or is it an actual real difference? We don't know this for certain. All we have is this p-value, which says, what is the likelihood that the difference that we're seeing, right? Because you're always going to have like differences. Is it actually because the 2 groups are truly different, or is it because of random chance? Does that make sense? So a p-value of 0.05, as Hannah pointed out, says there's a 0.05 chance, meaning a 5% chance, that the difference seen between 2 groups is due to random chance, as opposed to there's a 95% chance that the 2 groups are actually different. The difference is actually real and not random. Does that make sense? I also want to point out, Haley, I didn't mean to pick on you earlier. I hope it didn't come across that way. Although in retrospect, maybe that's what it sounded like. I find that I thought you gave a very good definition. It was, I think, just it's hard when, like, to people that don't understand it, it's hard to explain things. And I don't think I gave a much better of a definition, to be honest.
Oh, it's okay.
I just don't want you to think I was picking on you. That was not my
No.
I will
No,
tell you if I'm picking on you. I usually
It'll
warn
take more than
people. Okay, sounds good. All right, well, I will pick on you next. So, Haley, why do we choose a p-value of 0.05 as statistically significant? Right, because that's like the magic number. So, like, why? What the heck? What the heck?
Okay, so I think that might be going back to I think it was what Isabel said earlier about the standard deviations, maybe. And with that 0.05, you're so far out on the bell curve that like the chances are rare enough that we kind of accept that.
Ooh, man. Your definition was almost like Isabel's. Like, it sounds so good. Like, it's like the perfect med student answer. It sounds very good, but it's not very specific. So try and be a little bit more specific with your definition.
Okay. So I guess that means that we're 95% sure that the difference is real.
Yeah.
And I guess
why
90%.
95%? Why, like, what's so magic about that?
I don't know how that happened.
Yeah, exactly. That's because there is no magic. It's arbitrary. It's completely
Sounds
arbitrary.
good enough.
It's entirely arbitrary. We could have chosen 0.01. There'd be a lot fewer positive studies in journals. That's for sure.
Oh, so maybe is this having to do then? Because if we lower our p-value, which I think is the alpha, we increase the chance of picking up a difference that isn't real instead.
Think about what you just said.
So
Again.
So if we increase our p, then we're likely to miss a value or a relationship that's real.
Increase, meaning like we went from 0.05 to 0.1.
Yeah.
Oh, sorry. So then, sorry, your first definition was, your first thing that you said was correct.
So it's like,
in other words, if we doubled our p-value, if we went from 0.05 to 0.1, what are we technically saying, Haley? Let's say that our p-value is 0.1. What does that actually mean?
So that means that there's a 1% chance that our
10%.
10%. Oh. Okay, yeah, 0.1. So yeah, so there's a 10% chance that it's due to random chance.
That what is
our
the
difference
random chance?
Our difference between the two groups is due to random chance.
Perfect. Yeah, because at core, what are these studies looking at?
If the difference between the groups is real.
Yeah, well, they're looking at are two groups different? That's ultimately what all these studies are looking at. Are these two groups different? By how much? And what's the likelihood? That's it. At core, that's what all studies are looking at. You take two or more groups and you say, are they different? And you try to figure out why they're different. That's pretty much it, right? When you think about medical research, pretty much it. But it's essentially arbitrary, right? The p-value of 0.05 is essentially arbitrary. We're saying that 1 in 20 times, we're okay. We're okay if in 1 in 20 times that the result is like we think that it's true that the two groups are actually different, but they're actually not. It's essentially what we're saying. It's kind of scary, like when you think about it, right? Like how many studies are in the New England Journal of Medicine? Yeah. Granted, the p-values aren't all 0.05, but I've had like deep conversations, and I call them deep because it wasn't me that was contributing to them. It was like other people, so I can say it. But they were like pretty deep. You know, like if you think about it, like how many studies are published, right? Definitely more than 20. And even if they on average had a p-value of 0.02, right? We're still saying that like two of them like are not true. That the differences that we're seeing between the two or more groups are actually because of random chance as opposed to because the groups are actually different, right? Landmark trials. It's kind of scary. And it's especially scary because when you think about like the way that research is done, again, I don't want to get too far off course, but if you really think about it, ideally what you would do is you would do another study to revalidate the original findings. The problem is that most people don't want to do that because, right, like who's going to want to publish like a repeat study of the same thing, right? Everyone's looking for novel, right? So oftentimes these big studies for long periods of time, that's it. Like they're like the one game in town. This is a big actual criticism of I think it was like SSRIs. So the way that like drug development works, at least my understanding of the way that like drug approval works, is that you need 2 positive studies in order to get approved, or that was like what they needed to get SSRIs approved for depression. So if you think about it, let's say that there was like the p-value was like 10%, right? Or let's say that there was no difference. If you did, let's say that the p-value was 10%. If you did 100 studies, 10 of them would show statistical significance. It's kind of scary, right? So you're not actually looking at, how to say this? You're not actually looking at the negative results, right? They don't have to publish the negative results. And that's one of the big criticisms of like pharmacology research or drug trials. They don't have to publish the negative results. You just need 2 positive trials. I think Jessica was going to say something.
No, I'm not saying anything.
It's kind of crazy though. Like if you think about statistics, right? All right. Questions before we move on? Nope. Okay. So in our brain cancer cell phone example, what if the relative risk is 3? What does this actually mean? J-Ho, what does this mean? If the relative risk is 3, what are we actually saying?
So we're talking about relative risk. So we're talking about the exposure first. So people who have a lot of cell phone use or people who use cell phones have a 3 times increased risk of having brain cancer versus people who don't use cell phones.
Yeah, basically. Yeah. And so, Mike, can you tell me, let's say that the p-value here is 0.03. So what does this mean?
3% of these were just due to random chance trials, I guess.
So this is, I think, the trap that a lot of medical students fall into, is that like you use enough of the correct words that it sounds correct, but when you really push at what you're saying, it's not technically true. So try again.
I'm not really sure, actually, what you're trying to go for.
So what does the p-value mean in general?
The p-value is random chance in a study.
Not entirely. Be a little bit more specific. The random chance of a study. Not sure I follow.
Not random chance, but the difference you see, for example, in the 3% of this is from random chance.
3%. That's not actually true. 3% is due to, no, that's not true. So p-value of 0.03 means that the difference seen between these 2 groups, in other words, people that use a lot of cell phones, people that don't use a lot of cell phones, it's the probability that the difference seen between the high cell phone use group and the low cell phone use group in developing brain cancer is due to random chance. Does that make sense? So it's not really the random chance. Sorry, Mike, I cut you off.
Yeah, it makes more sense.
So what if, so Mike, what would happen if my p-value were 0.1? What does that mean?
The probability of random difference seen is increased by 0.7%.
Try again.
If you increase it to 0.1.
Uh-huh.
So 10% probability the difference seen due to random chance between the high exposed, the high users and versus low users.
Yes, exactly. Yeah. So again, remember, at core, studies are looking at, they're asking the question, are these 2 groups different and by how much? That's essentially what every medical study is looking at. Are these 2 groups or 2 or more groups, are they different? That's it. So if we say that the p-value is 0.1, we're saying there's a 10% chance that the 2 groups, the differences seen between the 2 groups is due to random chance. Does that make sense? Again, this is why I think statistics is so challenging, is because it hinges on such specific and technical definitions, but the more specific and technical you get, the more confusing it gets. It's almost like a catch-22. It's It's tough.
Alec, I have a question.
Please.
If I have a study when my p-value is 3%, or I realize that 3% of my difference is arbitrary.
It's not necessarily that 3% of your difference is arbitrary. No.
No.
We're saying that there's a 3% chance, because you're always going to see a difference between two groups, right? Like when you look at the raw numbers, there's always going to be a difference, right? If you just compared like those two numbers. With a p-value of 0.03, what you're saying is that the difference that you see is due to, there's a 3% chance that the difference that you see is due to random chance.
Yeah.
It does not mean that 3% of the difference is because of random chance. That is something that's actually different.
Okay.
It sounds, again, it's like the difference between odds ratio and relative risk. They sound so similar that you can kind of convince yourself that they're the same thing, but they're not. They're actually quite different. Subtle, but different. Same thing here. We're not saying that the 3% of the difference seen is due to random chance. It's not what we're saying.
Okay.
We're saying that the chance that the difference is seen is due to random chance is 3%.
Okay.
Like if your head is hurting right now, it means you're probably thinking about it properly. Like you're like moving in the right direction. This is like, again, probably the second most difficult concept in this entire presentation, the idea of p-value. It hurts my brain. So can you explain to me again, what does the p-value mean?
Is the difference related with the random chance?
Close. So let's say the p-value is 5%. What does that actually mean?
5% is statistically significance. It means that 5% of difference in my study is related with random chance.
No.
Hard.
I want to give someone else. So I don't think I'm doing, so the problem is me. I am not explaining it well enough. So I want to give someone else the opportunity to explain this because I don't think I'm doing a very good job.
Could I try?
Please.
Maybe? So the way I'm thinking of it is that instead of thinking of it as like the 3% chance, I think of it as if I were to run this test 100 times, 3 of those times, the difference between the two groups would be because of random things, whereas 97 times it would be because there's an actual difference between the two groups. Instead of thinking of the results, I'm thinking about if I run the test 100 times in terms of p-value.
Can you think about it that way? I think that's true. It certainly makes much more intuitive sense.
Because it's not necessarily saying that 3% of, it's not like when I run the test and I get 100 people, 100, that 3% of the differences that I find are due to random chance. What you're saying is that there's a chance that the results you're finding are due to random chance. I don't know if I confuse people more.
Or I guess I would think about it maybe this way. If you did 100 similar experiments, if you saw the exact same, like these exact same results, 3 times, the differences seen would actually not be real. They would actually be due to random chance. 97 of the experiments, the differences seen would actually be real. In other words, they would not be due to random chance. Patricia, does that help?
Yeah, thank you so much. I will study hard after the class, so thank you.
I promise that we will have more sessions on this. So we will put p-value in our next session. We'll figure out a way. Because this is tough. Caitlin, can you tell me, so what kind of study must this be? Is this a case control study or a cohort study, and why?
So since we were looking at relative risk, this is a cohort study.
Perfect. So Caitlin, so it's a pretty big relative risk, honestly. Like, so now we're sort of digging down a little bit, right? 3 times, as Jeho pointed out, there's a 3 times greater likelihood of developing brain cancer if you're exposed to high cell phone usage. The p-value is kind of high, like 0.03, honestly, for such a high relative risk, that seems kind of high. So how can you reconcile these two things? How could you have a higher p-value for such a high relative risk? What would be like a common thing?
I understand that it would be related to sample size, but I can't kind of reason out which direction the sample size would go.
Oh, I see.
If that makes sense.
Can someone help? So Caitlin pointed out correctly that that somehow sample size is going to affect the p-value. In the vast majority of cases, that's going to be true. But how?
So have a larger sample size, you can have a reasonably, or I guess it could be a more reliable lower p-value because you're repeating the test over and over and over more times. And so the chance of there being some sort of random difference is less likely when you have a larger sample size.
Perfect. Does that make sense? So in other words,
that makes sense.
Yeah, if you've done like 100, if your sample size is like 100,000, right, and you're seeing a very clear difference, the likelihood that the difference that you see is due to random chance is exceedingly low. Does that make sense? So the p-value for, if the larger the sample size, usually the lower the p-value, if there is a statistically significant difference. Cool?
Right. The thing that I guess that just tripped me up with that was that a 0.03 p-value is lower.
It is low, but honestly, relative risk of 3 is quite high. Right? Meaning there's a huge difference between those two groups. Right? There's a 3 times greater risk of developing brain cancer. So again, it's all about interpreting in context. Is that fair? So again, it's all relative, right? So you're saying, well, 0.03 is less than 0.05. That's still low, right? Yeah. But I mean, like, what if the relative risk was 10 and your p-value was 0.05? That's a pretty, it's a huge difference between two groups. And yes, while technically the p-value is 0.05 or less, it's not like I would expect that if there was such a huge difference, if there was a 10 times greater likelihood of developing brain cancer if you're exposed versus not exposed, I'd expect the p-value to be much lower. In other words, it'd be like a fraction of a percent as opposed to 3%.
Oh, okay. That's what I was going to ask. What is the cutoff? When do you say that the relative risk is high or not high?
I see. That's fair. I guess it depends on how you look at it. It depends on the context. 3 is high. 3 is definitely high. Because think about what relative risk means. As Jeho pointed out, it says that the risk of developing or the probability of developing brain cancer in someone that's exposed to high cell phone use is 3 times higher than if you have low cell phone use. That's a lot. That's a pretty big difference between the two. I mean, think about it this way. If you were to think about if someone were to give you a pill and say, hey, if you take this pill, your risk of developing brain cancer will increase by 3-fold. Does that seem high to you or not?
Yeah, I guess. Okay.
So I mean, this is sort of, this isn't I wouldn't have an absolute cutoff. This is more of you can use your common sense for this kind of thing. I don't mean that in a derogatory way. I mean you don't have to memorize this. So if someone said, hey, you have a 3 times greater risk of developing brain cancer, do you want to do this? Three times seems really high to me.
So if I'm getting this right, you should see a p-value of 0.01 because the difference seen between the high cell phone users and low cell phone users shouldn't be due to random chance if the relative risk is 10 times greater.
Correct. Yeah, exactly. I mean, it's possible to have a p-value of 0.03 with any relative risk, no matter how high it is, right? Even if the relative risk was 20, it's still technically possible. But again, the reason why I'm bringing this up is because a not uncommon question for the USMLEs is to ask, how can you see a difference between two groups, but the p-value is still high or something like that? Or what could you change? What could you change about a study to decrease the p-value? The answer in almost all of those cases is, go ahead.
Sorry. I think what tripped me up a little bit is you were kind of asking a question that wouldn't be a typical scenario. Is that correct? Is that why you were asking what would make the p-value not be what you would expect?
Correct.
Kind of
yeah.
Okay.
Because I would expect, honestly, the relative risk of 3 is pretty high. right? You're saying that there's a pretty big difference between those two groups. So usually for those sorts of, I guess maybe it's because I've done a fair amount of research. So I at least for a while looked at a lot of p-values. And usually when there's a clear difference between two groups, the p-value is like 0.01 or 0.001. It's like it's exceedingly low. 0.03 just seems high. But if you haven't read a lot of like research studies, this is a subtler point. This would be like a higher level. This is like a higher level understanding. But yes, when I wrote these numbers down, I was like, p-value of 0.03. That actually honestly seems kind of high. I was like, well, I'll go with it. And then I think you should be aware that seems kind of, I don't want to focus too much on this. I think it's unlikely that they would ask this specific question. What I did want to talk about was the effect of sample size on p-value. The important thing for you to understand is the larger the sample size, right? The larger the groups, the more people that you're looking at, the lower the p-value generally, right? The way that you can get a high p-value, even though you could see a big difference between two groups, is if the sample size were low. Because the point is that you can develop one patient that develops brain cancer in like one of the groups could make a big difference in the statistics. Does this make sense? I don't want to fixate too much on this. That was not my intent. The goal, the take-home message is sample size has a large impact on the p-value. Cool. I want to stop this here because I want to talk about questions before we go on. So we'll talk about type 1 error, type 2 error, and talk about actually using these things to design a different kind of study next time, as well as some other statistics stuff. But I want to stop here because we covered a lot of stuff, like a crazy amount of stuff. So I want to answer any questions that you guys have that came up, is what we discussed. Because again, I just threw a lot of information at you. I think based on some of your responses, I don't think I did a very good job of explaining some of it. And that's on me. So I want to make sure that I can rectify that before I send you off to read through this PowerPoint again. And if no one volunteers questions, I'm going to call on you guys randomly and ask you questions.
The thing is, right now, I don't know what to ask anymore. It's just all there, and I don't know if I get it all or not. I don't know.
Okay. So I think the easiest way is to go through, so after this, go through the examples that we gave and see if you can come up with the examples yourself, right? So in other words, can you design a case control study looking at the relationship between brain cancer and cell phone use? Can you design a cohort study looking at those two things? I actually, later on in the PowerPoint, we won't go over it today, but there is, we will talk about like designing, how would you design like a case control study to look at smoking and lung cancer development? Because that's a pretty classic one.
Hi, Alec. I do have a question about something that but I kind of don't want to confuse the rest of the group. So you can kind of make the call of whether or not you want to go in there, get into it.
Okay.
So you briefly mentioned about how p-values and how like smaller sample size gets more. If you have a smaller sample size, you're likely to have a larger p-value just because there's like a higher chance. There's a higher probability that whatever result you had is just by chance. And so, if I remember correctly, there was something about like the concept of power, where like that also is related to sample. Like if you have a larger sample size, you also have higher power. And I wasn't sure if that concept of power is related to what you were saying about like p-values and sample size, if that makes sense.
Let's talk about that next time, because we haven't talked about type 1 or type 2 error, and that's really, type 2 error is really, I don't want to confuse people. So let's remember that question. We will talk about that next time. Is that fair? But for you to know, I mean, if you think about it, the larger the sample size, the less likely that you will have type 2 error. Right? If you think statistically power is just 1 minus the type 2 error rate, right? So 1 minus beta. So that should make sense. Other questions? So I think at this point, your minds are probably spinning. That's totally understandable. What I would do is I would go to the integration and application question. So the way to know if you get it is twofold. One is I have gone through and created integration and application questions for you that will test you to see, do you understand it? So I would go through those integration and application questions in the beginning and test yourself. And again, you want to be ruthless in evaluating your own answers. I think statistics, more than maybe any other subject for step 1, is one of those things where we'll say enough of the right words that we can kind of convince ourselves that we get it. But then when push comes to shove, we don't actually. So you said, where can you find them? So in the PowerPoint, it's just, I think Haley pointed out. So in every PowerPoint, it's usually the second slide, right? So do you understand? So what is the difference between a case control study and a cohort study in terms of what they look at? For what kind of studies do you call bias most important and why? Like, why would that make sense? What exactly does the odds ratio mean? What's the difference between an odds ratio of 2 and a relative risk of 2? Again, if you can explain these questions, it means that you do understand the concepts, at least reasonably well. The other thing that I would do is I want you, again, design studies where you actually design like a case control study looking at the relationship between lung cancer and smoking, a prospective cohort study, a cross-sectional study, a randomized controlled trial, right? So again, I think that this is one of those things where you probably will not walk away with a perfect understanding. I actually don't expect you to. What I do expect you to do is, as soon as we're done, go through these integration application questions and make cards on them. And then be ready to discuss these next time. Sounds good? The other thing that I would do is I would start to do QBank questions specifically for statistics, because that's the best way to know, to assess how well you understand this. In either the next session or the section after that, depending on how much we're able to get through in our next session.
If you're serious about maximizing your scores, join our 14-day mini course now. We'll send you 14 high-yield videos that break down the exact concepts and test strategies our students use for 260+ scores. Click the link in the description below now to get instant access.
The difficult thing, I think, with statistics is that all of the different definitions sound so similar that it's really easy to convince yourself that they mean the same thing. So an example would be an odds ratio versus a relative risk. They sound really similar when you look at the definitions, and then when you get into the technical details, you're like, it just gets so confusing. So again, I want to just take a step back and remind ourselves what some of the fundamental themes of the statistics are. So the first is that, again, studies are looking at 3 things, right? So they're looking at exposure, they're looking at outcome, and the relationship or lack thereof between them. And that really, again, remember that research studies are really just asking the question, are the 2 groups, we're comparing 2 or sometimes more groups, we're saying, are they different or are they the same? At core, if you think about all the different studies that we've talked about, that's really what we're doing. And we're talking about the statistics involved. That's really what we're asking, right? P-value, right? We're asking, what is the likelihood that the difference seen between 2 groups is due to random chance or not, right? But again, the question that we're asking is, are these 2 groups different? Alternative hypothesis versus the null hypothesis. We're asking, are the 2 groups different? Alternative hypothesis. Or are they not different, which is the null hypothesis. Cool. So I think it's useful to take a step back and just remember, overall, what are we asking? All right, so I want to go through and I want to talk a little bit more about some of the stuff that we had ended on last time. I think that some people we were struggling with the p-value, which I think is a big challenge. So let's talk a little bit more about that. So again, the theme is that we're looking in studies, we're looking for differences between groups. So, Isabel, can you tell us what exactly does a p-value mean then in this context?
It translates into the confidence interval. So it gives you a measure of the likelihood that this result you've gotten is the actual result as opposed to the proportion that it came up by chance.
Okay, so I'm gonna need you to be a little bit more specific. So what do you mean by this result?
Okay, say you have a study that has an outcome that says your two groups are the same. Then if you've got a p-value of 0.05, that translates into a 95% confidence interval, which means that you're 95% confident that these two groups actually are statistically the same.
Interesting. I actually don't think that you use p-values to say if a group is the same. I think the p-value in almost every single case that I can think of, and someone can correct me if I'm wrong, but I'm pretty sure that the p-value is only to tell you that the two groups are different. It's the confidence that you have that the result that you're seeing. So in other words, the result, so you're saying that the result is either that we're saying the groups are the same or the groups are different.
Yeah, that was my impression, but actually now that you mention that, I'm not actually sure.
I don't think that's true. So instead, it's what you're saying is that you have the alternative hypothesis, which is that the two groups are different, right? And so remember, you're almost never going to get an identical value between two groups, right? So in other words, like if the height of one group is like, if you just randomly separated out two groups of people, even if you were completely random in the assignment, the two values of the average height between those two groups would still not be the exact same. They'd likely be very similar, but they're not going to be the exact same. And so the p-value tells you what is the likelihood that those two groups would be different. If the p-value, so given that, Isabel, how would you determine whether the two groups are different or not?
Based on the standard deviation or standard error of the mean.
Right, so based on that p-value.
Based on that p-value.
Right, so if the p-value is greater than 5%, again, and this is a completely arbitrary number, right? We have set the p-value at 5% as the number that we're willing to accept.
Oh, right, okay.
That if it's 5% or less, we're willing to accept and say that this is a statistically significant difference, meaning that we are willing to say that is the threshold necessary for saying the two groups are different.
So if you set your p-value and then if your p-value is larger than that, then they're not different. And if it's smaller than that, then you're 95% sure that they are actually different.
Correct.
Right, okay, sorry, I'm so used to looking at the actual bar graphs first, looking at the overlapping standard error of mean and trying to determine it by myself that way, and then looking at the p-value that I think I've gotten confused. So that's helpful.
So this was a pretty high-level discussion, though. So let's take a step back and see what questions that generated. Because again, this is tough. This is honestly, I find this stuff more challenging than like physiology or path. No one has any questions? All right, well, I'm going to pick on some people then to explain these. All right, so then Mitsu, what does a p-value of 0.05 mean?
That means 5% chance. Okay, there is a 5% chance that the difference observed between two is due to random chance.
Yeah, very good. Nice. Yeah, exactly. And then Kristen, can you tell me why do we choose a p-value of 0.05 as statistically significant?
We're saying that it's insignificant that 5 out of 100 times that the two groups are different when they're actually not.
Okay, good. So in other words, if the p-value, so what does that mean? So if the p-value is greater than 0.05, what does that mean relative to the null and alternative hypotheses?
It means that we fail to reject the null hypothesis. Oh, no, we reject the null hypothesis if it's above 0.05.
Meaning if it's like 0.1, like 10%. Let's say the p-value is try again. So what does a p-value of 0.1 mean?
It means that there is a 10% chance that the differences between the two groups are due to random chance.
Perfect. Okay, good. So if let's say that the p-value is 10%, right? 0.1. What does that mean relative to the null hypothesis? Do we accept the null or do we not reject it?
Well, we do not reject it.
Or I guess, well, how do we say this? Yeah, I guess we would say that, yeah, we cannot reject the null hypothesis. Yeah, good. Does that make sense? In other words, I guess we should say we cannot accept. We would not accept the alternative hypothesis. Okay, good. But remember, the p-value is essentially just an arbitrary number, right? We're essentially saying that 5% of the time we're okay believing that the two groups are different when actually they're not. But it's arbitrary. It's just a number that we chose. I'm sure that there's some historical reason why, but it was at core, it's just an arbitrary number. So let's talk through some of these other things. So what's type 1 error? So Sophia, what is type?
Sorry, Dr. Alex.
Oh yeah, please.
I have a question.
Yeah.
So could you please repeat it? When is above 0.05, the p-value, we reject the null hypothesis?
If it's less than 0.05, we do reject the null hypothesis. Right? We would accept the alternative hypothesis, right? Because we're saying that there's less than a 5% chance that the two groups, the difference that we see is due to random chance. So if it's less than 5%, we're saying that the two groups are actually different.
Okay.
Does that make sense?
Yes.
Great question. So Sophia, can you tell me what is type 1 error?
So it's if we accept the alternative hypothesis, we reject the null, but this turns out to be false. That turns out to be incorrect.
Okay. Perfect. Yeah. And why would it turn out to be incorrect?
Because in reality there is no difference between.
Yeah. But why did we think that there was a difference?
Because we fell into that margin of error that the p-value gives us. So the p-value would say there's a 5% chance that what you're seeing, the difference that you're seeing is occurring by chance. And we just happen to be in that 5%.
Perfect. Yes, exactly. Yeah. So if the p-value is 5%, then we're saying 5% of the time the difference will look like this, but it'll be because of random chance. So 5% of the time we'll think that they're different, but in reality, the difference that we see is just because of statistical chance. Right. And so type 1 error is when we incorrectly accept the alternative hypothesis is true. So Mike, what is alpha?
So I read it in first aid, but I haven't really been studying stats. But what we were just talking about, the rate at which it happens.
Rate at what happens?
Incorrectly accepting the alternative hypothesis.
Okay, so what's the difference between alpha and type 1 error?
I guess type 1 error is just a general term, whereas alpha is an actual number you can calculate.
Perfect. Love it. Yeah, exactly. It's the actual type 1 error rate, right? So similar, right? But again, this is why I find statistics so challenging, is because the terms are similar, but different.
Have you seen questions like distinguishing between that?
No. But I've certainly seen questions where they'll ask you like about type 1 error alpha. Okay. Yeah, I don't think, I find it unlikely that they would ask you a specific question on what the difference between type 1 error and alpha is. But I do think that it is important to understand the difference, because the better you understand the difference, the better you'll be able to do questions where they ask you about either of the two.
Right. Because I think it was a power question right after our last session 2 weeks ago, and I was kind of laughing about it because it was literally what we just learned.
Oh, that's good. All right. So Mackenzie, what is type 2 error? Oh, Mackenzie, you there? Oh, mic's not working. All right. Who are we going to pick on? Editha, what is type 2 error?
Okay. Type 2 error is the opposite of type 1 as I understand it, but okay, let me put it in words.
Good.
So if the null hypothesis, if we don't reject, okay, hold on. If we fail to reject the null hypothesis, when it is not true.
When it is not true. Yeah, good. Yeah, I honestly think type 2 error is the most confusing of all of the different terms. Yeah, so you fail to reject. It's a double negative, right? Anytime you have like these double negatives, it's like, especially when it's like a triple negative, it's you're failing to reject the null hypothesis when the null is false. Like that in and of itself is just, so let's take a step back. Let's think about this. So you fail to reject. So the null hypothesis says what, Editha?
It's false.
Oh, no. But what is the null hypothesis like in general? What does that mean? What?
Oh, okay. Null hypothesis means that there is no difference between the two groups.
Yeah, exactly. And so if you fail to reject it, right, when the null is false. So in other words, we're saying that the two groups are different.
But we don't. Okay, wait. They are different, but we don't see it.
It's like we fail to say that they're not different. Which again, I say that almost ironically because like if you're going to define it that way, it's really confusing. I think your definition is probably better, less precise, but I think there are so many negatives going on here that I think that's probably an easy way of thinking about it right now. But we fail to reject the null hypothesis. So in other words, let's say that the high cell phone user group and the low cell phone user group, let's say that there really is no effective cell phone use on brain cancer. Right?
Yeah.
Well, sorry, let's say that there is a difference between the two, right? So we should reject the null hypothesis. Let's say that there is an actual difference. But let's say that our study says that there's no difference.
Okay.
That would be type 2 error.
Type 2 error. Okay, yeah.
So then, Alicia, I know you just got here. Can you tell us, Alicia, and unmute yourself, and tell us what beta is?
I didn't get a chance to look at this before, but I think beta is, it's like 1 minus something, like, I don't remember.
Power is 1 minus beta. In this case, in words, what is beta? What does beta actually represent?
I don't remember. Sorry.
Okay, it's okay. Can someone help? Patricia, go for it.
Is the probability of you accepting the null hypothesis as a true when null hypothesis is incorrect?
Good, that's good. Yeah. So that's probably even better than what I was going to say, which was it's just the type 2 error rate, right? So it's the probability of failing to reject. Maybe there's like some subtlety that I don't really understand, but like failing to reject versus accepting the null hypothesis, like, I mean, I guess like they are technically different things, right? They're technically different things, but I think in practice they essentially mean the same thing. So Mackenzie's asking, alpha is what the researchers set correct, and p-value is what we get after running analysis. Yeah, well, we'll talk about this. So what's the alternative, Haley? What's an alternative way to describe the p-value using these error types?
Okay, so the p-value is the chance that our difference is due, the difference between the two groups is due to random chance. So that's kind of the same as the type 1 error, like incorrectly assuming there is a difference when there is none at all. So you could say that the p-value is the same as alpha.
Yeah, exactly. Yeah. So this is the most common thing that you guys are going to see. And this is again, like if you read like first aid, this is what first aid, like what a first aid type book would say. Now, I think it's important though to understand why that is, right? So Haley, can you describe again why that? I think that you did a great job. So can you just tell us again, why is p-value alpha?
Okay, so for the p-value, we're saying that in this, there's this small chance that the difference that we found between the two groups is really due to random occurrences, which is the kind of the same thing as saying that since the differences are due to randomness, the differences are not real and there's no difference there. So if you look to see the definition of type 1 error, that's kind of saying the same thing, that you're incorrectly finding a difference, or you're finding a difference when there is no true difference between the two groups.
Perfect. Yeah, that's great. Yeah, you've accepted the alternative hypothesis, meaning I've said I think that the two groups are different, when in fact they are not different. In other words, I'm making a type 1 error. I've incorrectly accepted the alternative hypothesis. I'm incorrectly saying that the two groups are different. This, honestly, is probably, in this entire slide, this is the most important question. This is what I consider an integration and application question. If I understand this question, right, if you understand this question, it means that you have to understand what a type 1 error is, and you have to understand what alpha is, and you have to understand what the p-value means. So if you want to have a good way of understanding, right, a good quick way of knowing, do I understand this topic or not, use these questions. And again, I lead just about all of these presentations with the integration and application questions, which you can see at the beginning of this one as well. Right, so all the PowerPoints are going to have these kinds of questions, where if you understand this one thing, again, you can assess and you can help reinforce your understanding of multiple different related topics, which is great. So Mackenzie asked, alpha is what really we set, and then p-value is what we get after running analysis. Yeah, essentially. I mean, yeah, I guess that's a way of thinking about it. Alpha, we set our alpha, or like we set the rate of type 1 error that we are willing to accept. And that, again, usually is a p-value of 0.05. But yeah, you could think of it as we're setting our alpha at 5%. Sometimes they choose 1%, depending on the again, that's like sort of the classic description. But when you get into like large data sets, then they set the p-values much, much, much lower. And they correct for the large data sets, but you don't really see that for USMLEs. All right, questions before we move on. This is, I think, one of the most challenging things that we're going to talk about. You guys are doing surprisingly well, by the way. Props. This is good. This is really good. Okay, so let's talk about some examples, because I think a lot of this, again, in going to questions and stuff like that, I think a lot of this is you just need to see it in multiple different ways. So let's say that in our example of cell phones and brain cancer, let's say that for a cohort study, our relative risk is 1.2 and our p-value is 0.04. So from this, Elise, which could you know? What have they sort of told you, the alpha or the beta?
Sorry, I didn't get that.
Which could you know from this in our example?
I know the alpha.
Okay, why?
Because they gave us the p-value.
Okay.
Which we said earlier was the, okay.
Yeah, good, exactly. And so, Mike, what does an alpha of 0.04 mean?
I'm going to phrase this wrong, but bear with me. The likelihood that there is a difference in 0.04, or I'm sorry, that there is a random error chance of 0.04.
Okay, so that's better than the last time, but it's still a little vague. So try again. So again, overall, we're trying to determine whether two groups are different. That's essentially what all studies are looking at. And then how different are they? That's how most of these studies are set up. Okay, so an alpha of 0.04, what does that mean?
There's a 4% chance that the difference observed is just random chance, like the alpha.
Perfect. Exactly. Yeah. Good. Does that make sense?
Yes.
Good.
I have a question.
Please.
Oh, okay. I guess that kind of answers it. So would we convert the alpha to a percentage just like we do the p-value?
Yeah. Yeah. Essentially.
Okay.
Yeah. Again, usually alpha, as Mackenzie sort of pointed out, usually alpha is sort of like, you can think of it as sort of like what we would accept. You don't, normally they wouldn't report like instead of saying like a p-value, they wouldn't necessarily say the alpha is 0.04. Certainly not in actual statistical studies, but even for like USMLE, I don't think they would ever say it like that. Usually the way that they use this is they'll say like the accepted like error rate would be 0.05%, or 0.05 or 5%. Yeah, that makes sense.
Oh, okay.
Usually you would not necessarily you would not say like, oh, the alpha is 0.04 in this situation. just so you guys know, again, I'm making this connection because I want you guys to see that they mean the same thing, and because you'll see that in like review books, p-value equals alpha. I want you to know why that is, but usually they will, like when they're reporting the statistics, they'll never say like, oh, the alpha is 0.04. I don't think I've ever seen that. Does that make sense? They would say like the accepted alpha is 5%.
Okay.
Okay, so in this case, Isabel, so would we reject the null and accept the alternative hypothesis in this case? And why or why not?
We'd accept the alternative hypothesis because the p-value is less than 0.05.
Yeah, exactly. Yeah, as long as we've sort of set our alpha, accepted alpha at 0.05. Good.
I have one more question just
Please.
to clarify.
Yeah.
So that rejecting the null hypothesis and accepting the alternative hypothesis are essentially the same.
They are the same. Yes.
Okay.
Great question.
Okay.
I was thinking about that last night. I actually like looked that up. I was like, does that mean the same thing? And it does.
Okay. Good.
Yeah. Because I was like, I know that it's described like that, but yeah. So that means the same thing. So in other words, Isabel, we can say, you don't have to say, oh, we accept the alternative hypothesis, but you can also say we reject the null hypothesis. These mean the same thing.
Got it.
And so why, Patricia, why can we reject the null hypothesis / accept the alternative hypothesis in this case?
Why what? Sorry.
Why do we reject the null hypothesis in this case, where the relative risk is 1.2 and the p-value is 0.04?
Because I have an alpha error when it means that I reject the null hypothesis as true and accept the alternative hypothesis null hypothesis as wrong and accept the alternative hypothesis as true. And this is because it is due to random chance. My error is related to random chance. Am I
so
correct?
the last part is what I didn't understand. So you said my error is due to random chance, but what does that mean? How did we note that we can reject the null?
Because P is equal to alpha. I have a 4% of alpha. So I have mistake. My difference is aleatory because it's due to P value. No?
Okay, so but why? Yes. So in other words, you're saying because the p-value is less than our arbitrary 5%, that it means that we are willing to say that the alternative hypothesis is correct. In other words, we're willing to say that the true groups are different.
Mm-hmm.
Is that what you're saying? I don't want to put words in your mouth.
I don't know how to explain, sorry.
It's okay. So again, so the thing that matters is what is the p-value, right? That is how we know whether we can reject the null hypothesis or accept the alternative hypothesis. It's all based on the p-value. For p-value is 0.04, we know that, well, again, we've set our p-value, our arbitrary p-value that we're willing to accept as the cutoff for whether we accept the alternative or not at 0.05. So in other words, if the p-value is less than 0.05, we say that the alternative hypothesis is correct. Very general sense.
Thank you.
Does that make sense?
Yeah.
All right. What's the alpha in this case and what's the meaning? So relative risk is 1.2, p-value is 0.06.
The alpha is a p-value, right?
So what is it? What's the number?
It's 0.06.
Perfect. Yeah. All right. So in this case, then, Kristen, are we going to reject the null and accept the alternative hypothesis? Why or why not?
We reject the null because if we were to set our p-value to 0.05, 0.06 is larger, and that means that there's a 6% chance that the difference we see is due to chance alone when actually the two groups are different.
Wait, so would we reject the null or would we not reject the null?
We would reject the null.
So in other words, we would accept the alternative hypothesis. We're saying that the G
Yeah,
groups are different.
sorry. I learned it the double negative way. So like I always use like reject or fail to reject. So to think of it as accepting the alternative hypothesis is kind of weird for me.
I see. So I actually, we in this case, we would not accept the alternative hypothesis. Right?
We reject the null hypothesis.
No, we would accept, we would not reject the null hypothesis.
Okay.
Why? So why would we not reject the null hypothesis in this case? Because if we reject the null, what are we saying? We're saying that the two groups are different.
Right. Yes.
Can we say that in this case? Or why could we say that in this case?
Okay, so we are not rejecting the null.
Correct.
And the null says that the two groups are the same.
Correct. Or they're not different.
So because the p-value is above 0.05, we're saying that there is a difference, right?
No. Because the p-value is above 0.05, we're saying there is no difference. This is tough, right? So when the p-value was 0.04, it was less than the p-value was less than 0.05, our arbitrary 0.05. So in that case, we could reject the null. In other words, we could accept the alternative hypothesis. In other words, we could say that the two groups are different.
Oh, so below 0.05 we reject, and above we fail to reject.
Yes, exactly. So again, the mistake that I think you're making is the mistake that all med students make, most med students make, which is that it sounds like you just memorized it. You're like, oh, above or below. Oh, it's like got a 50-50 shot. Is it above or below? Instead, if you make sense of what the p-value means, you'll never, ever forget whether it's above or below.
Okay.
Right? So what does the p-value mean?
That there is a whatever percent chance that the two groups are due to chance alone. The difference between the two groups are due to chance
alone. So again, think about so now it's like a physics problem. You want to think of the extreme, and then the gradations will make sense. So let's say that the p-value is 0.8. So what does that mean?
That there's an 80% chance that the difference between the two groups are due to chance.
Right. So in other words, 0.8 is well above 0.05.
Right.
So if you ever can't remember, like, oh, is it above 0.05 or below 0.05? That's statistical significance. Just think of an extreme example.
Okay.
Right. Obviously, we're not going to say that if there's an 80% chance that the difference seen is due to random chance, no way that we're going to call it statistically significant. Kristen, does this make sense?
It does.
Okay.
Yeah, I think I just had it reversed.
Yeah, exactly. No, totally. It makes total sense. The reason why I would be willing to bet is because you memorized it like everyone else did.
Yeah.
Right?
Can I comment on this?
The difference, yeah, please.
Because the way I like to look at it, and I think it makes it a little bit easier, maybe it will for her, is looking at it more of is it a 95% chance that my research is statistically accurate? Or is it, and because the 5% is the chance I'm going to make an error, accept a null.
95% chance is like the chance that I'm right. Yeah, you can think about it.
Yeah, basically.
Yeah. Sure. I think there may be some like statistical nuance that maybe that doesn't encompass, but yeah, grossly speaking, that is true, right? The lower the p-value, so in other words, if my chance of error is 5%, my chance of being right is like 95%. Maybe that would help too. That's another way of thinking about it, Kristen. But again, my general charge to all of you, I don't want to just pick on Kristen, but my general charge to all of you guys is the better you understand it, the less that you'll get caught up in these things where you're like, oh, I can't remember, is it like above or below? If you understand it, you'll never have to ask that question because it'll just make sense. Because again, on the day of your test, I guarantee you're going to start to doubt yourself. For things that you don't know well, you're going to doubt yourself. Like, you see it all the time. Students that like always finish with 5 or 10 minutes extra in UWorld blocks suddenly are like struggling to finish their like blocks on their real exam. Same amount of time, same number of questions. The reason is because you doubt yourself just a little bit more on everything. And so you spend a little bit extra time. The way to combat that is that the better you understand it, the better you will be at saying, no, I know this. Like Mackenzie said, there's like multiple ways that I can think about this. I'm confident that if the p-value is it's p-value of less than 0.05, that's just statistically significant. Perfect. All right. So this is another really, I mean, real life thing, but also an important thing that's tested on step 1, statistical significance versus clinical significance. So let's, who am I going to pick on? We'll go, how about Mackenzie? So Mackenzie, what exactly does it mean if something's statistically significant?
I mean, usually if you're doing research, it's that you've done a statistical analysis that says, you know, you're confident that.
Yeah, but what exactly does that mean? A hard question, right? That's a hard question.
Yeah. That's based on, no, I'm going to make it sciencey.
So we set it as like the chances that the difference seen between the two groups is less than 0.05. But really what we're saying is that it's something statistically significant when we are confident in accepting the alternative hypothesis. Is that fair?
Or, yeah, and not making the type 1 error, basically.
Correct, yeah. And again, relatively confident, right? 5% or less confidence that, or 5% or less chance that we're wrong. Right? Okay, so how could something be, so I'm going to open this to everyone. So what's a situation, or how could something be statistically significant but not clinically significant? Can you think of like an example of what that might be?
So maybe just kind of broadly speaking, like think of the statistical significance as the mathematical calculations, like, okay, it has reached this criteria. There's only a 5% chance that our difference is not true. But at the end of the day, when you go to equate it to real life, it doesn't even matter.
Yeah. So give me an example. Good. I mean, I think that's a fair definition.
Okay. So like, for instance, maybe if they were testing like dandelion tea on the effects of blood pressure.
Great.
Like statistically, the people that drank the tea had a 2 milliliters per H2. I can't remember the units.
Units are important. I'm going to push you on that in the future.
Okay. 2 millimeters of mercury.
Good. Yeah.
And their systolic blood pressure dropped by 2 millimeters.
Yeah.
So statistically, the people that drank the tea varied from the people who did not drink the tea. But are you really going to start telling all of your patients to drink this tea every day, say 3 times a day, to get their blood pressure to drop by 2 millimeters?
Exactly. Yeah. And so how could you, this is sort of a separate question, a related question, but how, like, what sort of situations do you see statistical significance, but not real clinical significance? Like what allows, because under normal circumstances, like how could a study possibly tell the difference of like 2 millimeters mercury systolic pressure difference? It's such a tiny difference.
If they have really precise measurements.
Okay. But also what?
Is it has to do with their power?
Yeah. Yeah. Which is related to what?
Sample size.
Sample size. Yeah. So in other words, if I had like 10 people in each group, no way I could detect the difference of 2 millimeters mercury systolic difference. But if I had
did
like
it with 20,000
2 million,
people.
yeah, I could probably do it. You could detect like even tiny differences that may not be clinically significant. So I think the example I gave was what if you just stopped taking any sort of salt, like you just had no sodium, you could maybe decrease your average systolic. Like what if you could decrease your systolics by like 5 millimeters of mercury? P-value is low, but like, would you really want to do that? Would you really want to decrease your salt intake by 90%?
No.
Yeah, no way. gosh, I think I would struggle with even a 10% reduction. This is why, like, I really hope I don't develop like diabetes or need to take diuretics for a long time. Because, man, just the dietary restrictions. Oh, don't think I could do it. There was I was told, I didn't do this, but I was told that, so like there's different, when you're in the hospital, there's different, I don't know if I should record this. There's different like dietary restrictions, right? So diabetics or like controlled carb, and people that are in heart failure have like a reduced sodium. But there's like, so people with kidney failure need like a lot of restrictions, because not only can they not have a lot of sodium because they can't deal with the salt load, but if their kidney failure is bad enough, then they can't have like certain like electrolytes and other stuff, right? They just cannot deal with like high potassium loads, for example, or other things, phosphate. And so it's like the nastiest food. Like hospital food in itself is not like great, but like it's like the worst food in the hospital. So there have been stories of people who would push maybe questionable diets on patients as a way of like encourage, because like some patients like will say like will refuse to leave because they really like being, I don't know, I guess they like being in the hospital or something. So I have known of people who have maybe used a slight increase in creatinine as a justification for giving someone a renal restricted diet. I say that not because I want to encourage you to do that. I say that because, again, I think that it's a way that you can help understand the physiology. And I'll just leave it at that. It is kind of funny. All right. Let's design our own study, shall we? So let's say it's 1960, and let's say that only 1/3 of all doctors believe that cigarettes cause lung cancer. And presumably 2/3 of doctors smoke. So how would you design a series of studies to prove it? Right? So how would you do it? Right? So in other words, let's say that I wanted to make a case control study. So Elise, how would you, so this is tough. This is probably the hardest question I'm going to ask. So how would you design a case control study where you would try to prove that there is a relationship between cigarette smoking and lung cancer?
First of all, you said my name right. That was the first time I hear my name right.
That's great. Oh, I'm glad. I assume that you're French.
Yeah, I speak French.
Yeah,
Okay.
I was a French minor, so that's why.
Oh, makes sense. Okay.
So how would you design a case control study, Elise?
The case control, we take the disease as our case and the control the people that do not have the disease, right?
So how would we design it? So I think the most useful way to learn these studies is to actually think like, okay, they gave me $1 million. Like, what would I do? Like, how would I actually go about doing the study?
Okay. So if we take the patient that had the disease, so patient that have lung cancer, and we compare them with patients that do not have the disease, so patients that do not have lung cancer. And we're trying to find which group smoke cigarette.
We're trying to find the rate of cigarette smoking, the amount that they smoke in each group.
Okay.
Good.
And then we compare, yeah.
Yeah, good. Yeah, exactly. So take people, so in other words, but we start with people where we would look for people with lung cancer, and then we do matched controls who do not have lung cancer. Then we'd talk to them, or interview them, or survey them, or whatever. And we'd look backwards in time. Wait, this is a retrospective study. Backwards in time and assess their smoking history. Good. Perfect. All right. Editha, how would you measure the relationship between the outcome and the exposure?
Odds ratio.
Oh, perfect. Love it. And in words, what would the odds ratio tell you in this specific example? Editha?
Okay. Odds ratio would tell me. Gosh. I don't know how to explain it.
Then it means you don't understand it.
Okay.
In general, I think that's true. I mean, I'm not trying to pick on you. But in general, that's a good way, like one of the most important questions in the beginning when people are learning this is, mastering the topic or not? And if you can't explain it, if you can't teach it to someone, means like that to me is always a sign that I don't understand something. I have not mastered it yet.
Okay, all right, let me try. The people with lung cancer and the people without lung cancer, we compare how much they smoke. So the odds ratio would tell us what are the odds that the people with lung cancer smoked in the past in comparison with people without lung cancer.
Wow, that was great. I don't know. I mean, like everyone else is muted, but I'm sure that
Really?
they're all like jaws dropped. Like that was great. That was fantastic.
Awesome.
That was
Cool,
good. Well done. Yeah, exactly. So in other words, it's the odds that people with lung cancer smoked in the past relative to the smoking rate of people who do not have lung cancer.
Yay.
Great. That was really good. Well done.
Thanks.
Well done. All right. So let's make this more interesting. Kristen, how would I design a cohort study?
So you're looking at the exposure here. So you take people who smoke versus people who don't smoke and follow them, or you could do a retrospective study.
But usually
a
it's
prospective
Let's
study.
design a prospective.
Okay. Well, you would see which people develop lung cancer. And then so you're basically looking at the exposure, smokers versus non-smokers, and who develops the disease.
Yeah, and again, it's not really who develops it, because again, presumably both groups are going to develop it, but you're looking at the rate of developing lung cancer. Right? It's not, no study is going to be like everyone gets disease in one group, no one gets a disease in the other group. That's pretty uncommon. Yeah, it's the rate of the disease. But yeah, good. And then Patricia, how would you measure the relationship between the outcome and the exposure?
Between the relative risk.
Yeah, good, exactly. And so what would the relative risk in words be, Patricia, in this case for our prospective cohort study?
We will analyze who was exposure to cigarette and analyze prospectively who will develop the disease.
So that's our design. I'm asking you, what would the relative risk describe?
And describe the relation between people with disease and exposure in relation with people without disease and no exposure, people with disease without exposure, and people.
Sounds like you memorized. That also sounds very similar to odds ratio, not relative risk. So try for relative risk. So odds ratio is looking at people with disease and looking backwards in time and looking at the odds that they were exposed or not exposed. This is different. Remember, relative risk is a forward-looking thing, right? So people that smoke versus not smoke, looking forward. So what would the relative risk be? Again, using these specific examples.
What will be the risk that the people that smoke in the past will develop the lung cancer?
Perfect. Yeah, exactly. Yeah. Relative to who?
Relative to
what? Yeah. Relative to what?
Just exposure.
Relative to the risk of people that don't smoke developing.
Oh, yes, of course.
Because again, you're always comparing most of these things, right? You're comparing two groups. Does that make sense? Again, case control cohort, I think that's like probably the most challenging thing. That's like probably the hardest thing. But all this stuff I find very challenging because it doesn't necessarily, none of this stuff makes intuitive sense. It's not like, you can't like see it in real life. It's not like the baroreceptor reflex where it's like you can see it. Right? It's like kind of abstract. Good. Okay. So Isabel, how would I design a cross-sectional study?
It's in present time, so you randomly choose two populations and look at the rates of a disease in those different populations. I mean, you could use it to assess something like
So how would you actually do it?
exposure.
So like in this case, we're trying to prove that there's a relationship between, because I mean, really, like all these studies, that's what you're trying to prove relationships, right? So there are different pros and cons of them, but how would I design a cross-sectional study?
To do with smoking and lung cancer. I don't know. I find that kind of slightly more difficult, but you could take a group of patients that have lung cancer and see whether they smoke now versus I don't know. I think I'm confused as to how you do that, because that would be very biased, because if you have a group of people that smoke, they probably wouldn't be smoking even though that was a risk factor in the first place.
Wait,
You know
what?
what I mean?
You mean if you had a group of people with lung cancer, there's a likelihood that they would have stopped smoking. You know?
Yeah, exactly.
Yeah, exactly. So again, I'm not saying that any of these studies are ethical or would be good. I'm just asking, how would you design it?
Oh, right. Okay.
So I'm not saying that, again, because I think what you're seeing is that some of these studies are good in some circumstances and not in others.
Yeah, so I don't think this one works at all in this circumstance, but
yeah, but how would you design it?
I mean, you could go into a hospital and take a group of the patients in the hospital that have lung cancer, and a group of patients in the hospital that have a different disease, and look at the rate of how many of them smoke in each of the groups.
Perfect. Yeah, exactly. Yeah. Again, I agree. Probably not a great way, because again, if you smoked and then you develop lung cancer, but again, in the 60s, this might have been a reasonable thing. This could have been a reasonable study, right? Because
it would be I was thinking it would be much better for geographical exposures. For example, taking a group of women in their 40s in Scotland versus a group of women in their 40s in America and measuring the rate of MS, for example. That would work better for a cross-sectional.
Yes. Yeah. Good. Nice. Good. So you're starting to think about the different, thinking more deeply about the studies. That's ultimately what I want you to be able to do. So again, this is a very ethically challenged study. I don't think you would ever do this, but let's say, what if you were to design a randomized controlled trial, Sophia? How would you do it?
So you would take, let's say, 100 people, then you would assign 50 to smoke, randomly assign 50 to smoke and 50 not to smoke, and then you would follow them prospectively and see who developed lung cancer.
Yeah, or how many people develop lung cancer. Yeah, exactly. I mean, obviously, this would not be done. Would have a really hard time convincing any ethical boards to this, but that's how you would do it. Obviously, RCTs are much more for treating disease rather than causing it, so it sounds sort of silly in this situation, but that's how you do it. That's one way you could do it. Good. All right. So let's talk about a couple more applications. So Mackenzie, what's the difference? What exactly does an odds ratio of 2 versus a relative risk of 2 mean when we're talking about the link between cell phone use and brain cancer?
Okay, so the relative risk would be of 2. It's over 1, so you actually have a risk of developing brain cancer. The odds ratio.
Words specifically.
So compared to people who didn't use cell phones, you have a greater risk of developing brain cancer when using a cell phone. And then for the odds ratio,
How much is the greater risk?
2 times.
Good. Perfect. Yeah.
And then the odds ratio is the odds of, so people with people who use cell phones, that's more risk. You have a more likelihood of developing brain cancer when using or the odds of developing brain cancer is more likely when using a cell phone than it would be when not using a cell phone.
No, that's not what it says. That's not what it says. This is why I asked this question. Again, integration and application question, right? This forces you to use it in exactly the way that people get it confused. So I kind of picked on you. I definitely picked on you.
No, it's good.
But again, if you understand these kinds of questions, you will have a much deeper understanding and have a much better chance of being able to answer whatever they throw at you, as opposed to just hoping that they happen to give you a question that's identical to what you saw in UWorld. Who can answer this? This is tough. So the relative risk was correct. Or go ahead.
Is it the odds of having cancer? So is 2 times compared to while using, like with using cell phones, compared to the odds of not having cancer with the use of cell phones?
Nope.
Okay.
Can I try to answer this? Oh, good.
Everyone wants to answer it.
Yeah, I think Mitsu thinks it spoke first.
Just okay, I'm gonna try it. The person who has brain cancer actually 2 times more than using the cell phone heavy than who doesn't have brain cancer to use to use cell phone heavy.
Perfect. Exactly. So in other words, what we're saying is that, so relative risk is a forward-looking thing, right? It's saying if I use a lot of cell phones, I have a 2 times greater risk of developing brain cancer, right? It's forward-looking. It's starting with the exposure and then going forward and looking at the development of disease. The odds ratio is actually a retrospective thing. So it's saying if I have the disease, if I have brain cancer, the odds are 2 times greater than in the past I used a lot of cell phones. Does that make sense? So this is the specific reason why I asked this question, right? Because it is like the most commonly misunderstood thing about odds ratio, right? So again, if you understand this, it means that you understand so much. Think about everything that goes into understanding this question. You have to understand the difference between a cohort and a case control study. You also have to understand the difference between relative risk and odds ratio. This is a great question. With one question, you can remember like 4 or 5 different things and remember it in such a way that you can help differentiate between them. You can use it. This is much better than just making individual cards on what is a case control study, what is a cohort study, what does an odds ratio of 2 mean, right? You'd have to make like 10 cards to get the same amount of information as you could in just one. This is really powerful. So the more questions that you can have like this in your Anki cards and be doing every day, the better you will understand these things. Which is why the exact reason why I lead with questions like this in every single presentation that we do. And this is why I harp on you guys. Every single time you do videos, I say, did you make cards on the integration application questions? Did you make cards on the integration application questions in the beginning? Right? But this is it. Because think about all the things, just in the same way that understanding like what is equivalent to the p-value, alpha or beta, right? Understanding that, there's so much you have to understand in order to answer that question. Perfect. Haley, what if the relative risk is 1?
So if the relative risk is 1, that means that the 2 groups are equal.
What does that mean? It's still a little too
So, okay. So the relative risk, we're thinking, looking forward. So the people who used high cell phone usage had a 1 times greater risk of developing brain cancer compared to those who didn't.
1 times greater meaning the same risk.
A rate, right? Yeah, exactly. There was no difference between the risk of developing brain cancer in the high cell phone usage and the low cell phone usage groups.
Perfect. Great. Does that make sense? What would the odds ratio of 1 mean?
That looking at the 2 groups with brain cancer and then the group without brain cancer, there was no difference in the likelihood of them using cell phones or not.
Yeah, in the past. Okay. Very good.
Now that you understand these core biostat concepts, you need to know how to apply them on test day. In this next video, you'll learn the framework that stops you from missing questions you actually know, and the exact test taking strategies that took students from failing to 260+. Click here to get how to virtually guarantee a 260+ on step 2.